continue on finding antiderivatives or integrating, we're going to integrate by substitution. So we talked about the anti-power rule, I think it was the last video or a couple of videos before. This is really an anti-chain rule. Remember that when you do the chain rule, if I took the derivative, got a chain rule, I would end up with f prime of g of x times g prime of x. That is, I would end up with a product. So when I'm going backwards, it's not the anti-product rule, it's actually an anti-chain rule. So the way to do this is the following. We're going to pick an appropriate function. We'll call it u, usually. You often hear me call it u substitution. And we'll let it equal g of x. Usually the function inside a function. What I'm really looking for is a bigger function that contains a smaller function and is multiplied by the derivative of the, I should say the inner function, multiplied by the derivative of the inner function. And then I'm going to let u equal that inner function. Why? Because if I take the derivative of u, I get du dx is g prime of x, of course. A little bit of algebra says, well then du is g prime of x dx. So I can do some substitution. Notice that f prime of g of x becomes f prime of u. G prime of d of x times d of x becomes exactly du. So this long, messy looking thing becomes something pretty simple, f prime of u du. I'm not saying it'll make sense, but hopefully it will up here when I do some examples. So I have a function inside another function, inner function, outer function, multiplied by a different function. Very often this is on the front as opposed to perhaps being on the back side. But my claim is I could let u equal x squared minus 1. Because if I do that, then I get du is 2x dx. And notice here, if I substitute in, this becomes u to the 1/2. 2x times dx becomes exactly du. And notice I have a much simpler function, just a power rule, which says I'm going to add 1 to the power, divide by the new power. So instead of dividing by 3/2, I will multiply by 2/3. And remember to put my constant of integration. Now I'm going to back substitute. Since I started with x's, I want to end with x's. Integration by substitution gives me that this is the integral. If I took the derivative of this correctly, with the chain out, I should end up back over here where I started. Let's just do some more examples. See if you can guess up here what I'm going to let u equal. Usually I let u be the thing inside parentheses or somehow imply that this is what it has to be. It's not always inside parentheses, as you'll see in this example. But worst case scenario, pick a u, find du, and then see if it works. Well, let's see. Does it work? Well, if I plug in, I get u to the 5th, and then I need 3x squared times dx to equal du. I don't have 3x squared. I have x squared. I'm off by a factor of 3. Now, if you're off by a multiple of a constant, it's okay. I can just multiply by that constant. I have, of course, changed the equation. So to fix it, I'm going to multiply by 1/3. Notice that I've multiplied the expression by 1, so I haven't changed anything. The 3x squared dx becomes exactly du. I have a 1/3 left over, right? This 3 becomes absorbed into my du, but this 1/3 is left over. I'm down to a power rule. I have 1/3 u to the 6th over 6 plus c. Making it look nice, back substituting. I get my antiderivative. How about something like number 3? Well, let's try some stuff. What if I let u equal x squared? Then du would be 2x dx. Well, I don't have 2x dx anywhere. Being off by a number is fine. Being off by an x, not good. It just tells me I did the wrong thing. Let's try u equals negative 1 over x. Then du would be 1 over x squared dx. And notice I do have that. So substituting in, I have e to the u, and then dx over x squared is exactly du. Where the integral of e to the u is e to the u, so I'm just going to skip that step and back substitute. And there's my antiderivative. But what if I have limits? Recall that we did limits and we used the fundamental theorem of calculus, that it was implied that I have x equals 0 to x equals 1. We don't write that, we need to know it. I'm going to do the same idea. This is going to be my u. If you think a different u will work, try it. But notice, I have exactly du somewhere. That's a pretty good clue that I chose u correctly. And so writing it over here, I would have the integral of du over u to the 1/2. Now, my claim is that my limits will change. Now, how did I know to put 1 and 2 instead of 0 and 1? Well, everything was over here was x's. The function of x, dx, x equals to x equals. If I'm changing to u, everything should be u's. Implied a new function of u from u equals to u equals. But still, how did I know it's 1? Pretty simple. If x equals 0 and u is 1 plus x squared, then u is 1 plus 0 squared, or 1. If x equals 1, then u is 1 plus 1 squared, or 2. I will let you finish this problem. Just for the sake of time, let's take a look at this last one down here. I'm going to let u equals x cubed, giving me du is 3x squared dx. Notice that I have most of my du. I'm only off by a multiple. That is a constant multiple, so I can fix it by multiplying by 3 and by a third, so I don't change the expression. And then I have 1/3 e to the u du. Well, if u is x cubed, then if I start at x equals 1, I'll also start at u equals 1, right? 1 cubed is 1. If I end at x equals 2, I'll end at u equals 8. Actually, let me go back and finish both of these up for you. This is really u to the negative 1/2. I'll think that in my head, so I'll add 1 to the power, divide by the new power from 1 to 2. Plug in the top limit, minus plug in the bottom limit. I, of course, could simplify that, but I'll leave it as is, just so you can see where everything is coming from. Similarly here, taking the antiderivative, Then I'll plug in the top limits, minus plug in the bottom limits, and I get my answer.